this will hopefully tide you guys over in the interim, and Brian will be able to fix, or Dr. Woodrum rather, will be able to fix out or flesh out some of the other details. So what follows here are kind of my spin off the slides that you guys have seen, and I tried to cover the slides that Dr. Woodrum might not quite understand because I just see things weird, okay? And so that's not his fault, that's definitely me, I'm just a weirdo. Hopefully what you're seeing now below are also bookmarks. Feel free to click on these bookmarks to kind of skip through. We should be going through some syllabus stuff first and then kind of into the general background information. And I'll try and set you up with links out to other videos as necessary. So number one, I noticed that only about 6 students have signed up for SmartWork, and of those 6, only 2 or 3 actually are full registered users. So make sure you get signed up for your online homework system as soon as you can. The highest score on our final last semester found that doing the homework as early as possible before the exam actually resulted in higher marks on the exams. So try and get the homework done as early as possible. You will have to go through and set up that sign-up process. The software company that is running SmartWork is aware that I'm out, and they will hopefully be a little bit more responsive to help requests made through their website. For sure, what you will need to get enrolled is the enrollment key McFablin FA16 for our semester. Okay, so please get that going. When it comes to the homework, for those of you that aren't a fan of online homework, I gotta admit, I'm not the biggest fan either, but it does have a lot of very useful things to it. So to kind of counteract some of those negative aspects, I do adjust the homework grading accordingly. So in theory, our total homework points come out to 100. 60 of those points will come from our online homework. Okay, so if you look at your SmartWork score of 90 to 100%, you get full credit for the online homework, 60 points. So this gives you, per question, I think 2 free attempts without really risking hurting your homework grade. Notice that I've got the scale set up accordingly, or as shown here, so that you can kind of pick out what would end up happening. So if you scored, say, the 65% on the homework, which arguably isn't passing, gets you 50 points, okay, which is roughly a 90%, did I do that right? Sorry, an 80% as far as the homework grade goes. So as long as you're working on and doing it and getting most of the questions right, you should be okay. One thing I will say is that with your attempts, you get 3 attempts. Okay, and this number varies per student, but really 3 attempts. After that 3rd attempt, you need to be contacting me, or if I'm not there yet, Brian, and hopefully Brian can help, Dr. Woodrum can get that figured out. Okay, because really what happens is after 3 attempts, more than likely you're missing something, and we need to make sure you have what that is figured out before continuing to get through it. After 3 attempts, all you're going to start doing is blind guessing. That's not going to help you get through the homework, and that will end up hurting your score. So if you find that you get frustrated with the homework after 2 attempts, fine. Send me an email, copy Brian, Dr. Woodrum on it for the moment, and hopefully one of us will get back to you. I officially can't work after midnight tonight, so we'll see kind of what happens. And I should be out for about 2 weeks. So just to kind of give you a heads up. When it comes to the online homework, when we get back, I'll deal with whatever kind of grade issues may have popped up and account for that when we look at our final grades. So don't panic and think you're going to lose out there. The other big thing, you are required to do pencil and paper homework. You can do it in pen if you want as well. These homework questions can come from suggested homework, which I don't think I've got posted on Canvas, but I will get on Canvas as soon as possible here. They can come from the old exams, and they can come from the SmartWork stuff. As long as you are writing something down, that's what I want to see. And that's due every second week. So next week, Friday, you'll need to turn in a homework assignment. I'll make sure that Dr. Woodrum knows what's going on with that, and pretty much all that happens is I scan through it and say you attempted questions. We're looking at 10 questions attempted. They're not getting graded per se for correctness, they're just getting graded for completion. Did you do it? Okay, that will then account for another 40 points of your homework grade. So as long as you're doing that, you've got those points free. Kind of a new thing, and it's not perfectly set up in the syllabus that I had printed, was that there will be a variety of quizzes and group assignments throughout the semester. So I've been playing around with more and more activities and getting you guys to work together, because that is one of the things that has also improved scores, is students working together. So if I can get you working together in class, I'm going to do it. I'm going to incentivize that with points. Okay, so you'll see some kind of more assignment points weighted for that. There are 3 semester exams. I should be there for all of them. Again, the first one's going to be a bit questionable because you're using 2 different instructors. We'll account for that when it comes to grades. Don't panic. Okay. Every exam is by nature cumulative. Organic chemistry is a 1-year course that has been force broken into 2 separate semesters. It has then been further force broken into, depending on your instructor, 3, 4, 6 different kind of bite-sized chunks. Okay, so please realize that you are not looking at a new unit each time. You are looking at an additional piece of information that you need to know. Additional. That means everything from first semester you must know and you will continue to use. Everything that we use on exam 1 will show up on exam 2, will show up on exam 3, and will show up on the final this semester. Not perhaps explicitly, but to a certain extent it will be there. So make sure that you're preparing and constantly reviewing. The final exam is the ACS first semester, or sorry, that shouldn't say first semester. It is the 1-year organic chemistry exam. It is exceptionally difficult. That said, students last fall that went through the same instruction that you guys are getting this time in the same textbook did exceptionally well. Okay, the national average is in the 50th percentile. Okay, I was just at a conference where a lot of instructors were reporting averages for their classes in the 30 percentiles. Okay, so it is an exceptionally difficult exam. It requires practice. So keep working at it. You will get it, and you just kind of have to break through what I would say is kind of a stamina barrier. 70 questions on organic chemistry is a challenge in the sheer volume. Break it down into the slower pieces, and you'll be okay. Extra credit. Everybody wants this. For my former students, please step in if anybody has questions and kind of help out with this. I offer extra credit in 2 forms. One known as a dialogue. After 24 hours or within 24 hours of Monday or Wednesday's lecture, you send me an acceptable, quote-unquote, email describing what you learned in that class time and how long you've spent studying. Okay, that email needs to go to my CGC email, so michael.mcfavlin@cgc.edu, with the subject line DFA16CHM236. You should be getting an automatic response. If you get a more personalized response, that is because I didn't see it as an acceptable email. Okay, that is very, very rare, but be aware it can happen. You get one kind of free pass there. These do not have to be super long. A couple sentences is fine. Feel it out by testing the waters. See how I respond. You need to spit 9 of a possible 15. So it's only 1 every 2 weeks. That's really not that difficult to go through and do. The other option, for those of you that are already spending lots of time in the tutoring center, if you spend 2 hours per week in the tutoring center for 9 weeks out of, again, a possible 15, I will also give you this 2% bonus to your grade if it affects your grade at the end of the semester. Okay. To get this, you will have to sign into the computer. Hopefully the tutors or the Science Tutor Center came by and talked to you guys. For those of my old students, disseminate, get the new students in, people that aren't aware of what I do, and get them involved and bring them into the tutoring center if at all possible. Okay. Actually, I guess one more thing on the extra credit. The way this gets assigned is strictly extra credit. At the end of the semester, I assign grades, and I flag people that are borderline grades. Okay, so I say a 90 and above is an A. It's usually more like an 88. If someone scores, because I switched up the numbers, let's say 88 and above is an A. If you score an 86% in the class, well, that's officially a B. So you would get assigned a B. But you're within that 2% barrier, or that 2% line. So what I then do is go into my email, and I look for the dialogues, and I look for the amount of time you spent in the tutoring center. If you have achieved that, I add 2% to your grade. That puts you above the grade threshold, and you get the higher grade. Okay? So you do not get penalized for not doing the homework, as most instructors end up doing or do extra credit. This is strictly extra credit. You are not required to do it, though it is exceptionally highly encouraged and recommended that you do it. Both of these things are things that you should already be doing in the process of just taking the class. I'm just now providing a kind of small incentive to help you do that. Syllabus quiz. There is an online syllabus quiz. I haven't had time to check to see if people have been doing that or not. Please look for it. There is a due date of August 31st. I'll keep my eye on it, and if it doesn't look like people are completing it, I may extend that due date a couple days, and you'll see an announcement on Canvas about it. Second quiz. This is one of those kind of assignment things. I will give you 5 points towards your assignment or quiz grade by simply sending me your first extra credit assignment. Okay? Give me the subject line. Give me your preferred name so that when I get back I know what to call you and I'm not calling you by your full long name if you want to be called by something else. I want to know what you found to be really, really hard of OChem 1. I want to know if you think you belong in OChem 2. Okay? This is to get an idea of where you are. Kind of an imposter syndrome. Believe it or not, nobody feels like they belong. Okay? That's okay. We need to get through that. And then as an actual quiz question, there are 5 primary types of chemical reactions. I want to know what they are. Okay? So provide those 5 reactions or what you think those 5 reactions are. And as a hint here, not mechanism, reactions. Okay? Big topics from first semester. Okay, these are kind of the big, huge things. You should understand these topics and hopefully be able to manipulate relatively simple questions about them. So there are things known as electronic effects. This is largely due to resonance and electronegativity. So when we look at structures, we're going to be looking for atoms that are more electronegative first, because those will cause a polarity in the bond structure. That polarity increases the likelihood of an interaction happening around that site. Okay, so we're going to start to focus our attention there. So this is why electronegativity is important. On top of that, we can see what I would refer to as kind of a molecule effect as opposed to an atom or bond effect, and that's resonance. The electrons are dispersed throughout the molecule, and they will disperse themselves according to certain patterns and can move according to resonance. Okay? So it is an exceptionally important topic. Keep thinking about it, keep looking at it when you're going through your structures. Strengths of acids, bases, electrophiles, and nucleophiles. Okay, ultimately, all these are looking at are charges. Are we looking at a positive atom or a negative atom? Is it more positive? Is it less negative? How do these things kind of balance out? Okay, so you're going to need to go through and come up with an organized ranking system so you can identify quickly what kinds of reactivity there are. I've broken down ranking those things according to what I've listed here as 6 different things, though numbered really oddly. Charge is your first and foremost important thing. If you see something that is negatively charged, it's probably going to react as a negative, okay, just as a red flag. Atomic size, okay, we need to look at the size of the atom. Okay, if the atom is really, really big, how does that affect its reactivity as a positive or a negative? Atomic electronegativity, okay, how does that affect its charge as a positive or a negative? At this point, we've moved beyond atomic effects, and we now need to evaluate the molecule. And that's when we will look at molecule size, or ultimately resonance. How do the electrons disperse themselves throughout the molecule to generate different charges? We'll also look at an inductive effect. Okay, where are there more electronegative atoms, and how do those propagate an effect through the rest of the molecule? Okay. The last thing is hybridization, which hopefully we won't get into, but that's kind of a last-minute call. If we can't see an effect, we can start to look for these more difficult nuances to come up with differences in our reactivity. Okay. Next big thing, structural effects. Orbitals, stereochemistry, and sterics. Okay. These are all looking at pretty much how the molecule is shaped and how its shape allows it to react. Okay. So you need to be aware of what atomic orbitals there are, what hybridization theory is, and we'll get into a little bit of molecular orbital theory as well. Stereochemistry, where are atoms relative to other atoms? This is seeing in 3 dimensions, not easy, requires practice. This is why we do it in first semester. Sterics, what are the pieces? Where are those pieces? How do those things limit how a reaction can work? The next big part is really where we spend a lot of focus in second semester, though I try to just re-emphasize that everything we just talked about, those first, I guess, 3 or 4 things up here, are really the big topics. We then apply that into your reactions and mechanisms, which is your what versus your how. Okay? So kind of always look at the reactions, but say, okay, how does that go back to those primary categories? Okay? And that's going to be kind of our big topics from our first semester. Okay, I felt that this sequence of slides here might have been difficult for Dr. Woodrum to pick out because I don't think it's obvious necessarily how I was thinking about it. Okay, so what we're starting with in second semester is kind of a review of our addition reactions. Okay, and in particular, some things that can make them more challenging. So when we look at acids reacting with our addition reagents, if we kind of simplified our structure here a little bit and just did something like this, and we added, say, the strong acid HCl, well, we might be able to go through and hopefully say, well, the hydrogen will add out on the one side of this, and then our chlorine would add to the other side. Okay, and hopefully you've got that reagent sequence already memorized. If we went through a mechanism, hopefully you would realize that the most reactive thing here is the hydrogen, our H+. The electrons from the double bond come out, react to form a bond with our hydrogen, leaving a carbocation and our chloride ion floating around. This is where our charges come into play, because now we have 2 atoms with charges, and what do we need to do? We just need to bring the negative to that positive, and we've got our system set up and ready to run. Okay, so that was kind of first semester. What happens in second semester is we make things a little bit more difficult. You'll notice that what we've changed here is we've added a second double bond. Okay? And if we compare those 2 double bonds and say, well, what is the difference? We might say, well, there's no difference. Okay? And at this point, we'd be right. There is no difference. So we would pick either one to react with our strong acid. So because that first one is closer to the hydrogen, I'm going to pick that one, break the bond with our chlorine, and we should end up, and I think I drew that, no, I drew that okay. And if we wanted to show that hydrogen, we could, though those of you that are used to online homework should realize that that structure is going to come up wrong in an online homework system. because it thinks you're saying that that carbon only has 2 bonds. Okay, so if we're going to show that hydrogen, we should show the other hydrogens, and I'll show them as purple because they were there before. Okay. We still have that chloride floating around, so I'll erase that wrong. And that chloride, trust me, that's a Cl, could potentially react with that positive just as we saw before. Okay, and that is fine. That is a possible product. But before we start pushing that, what we now need to also do is say, are there other things that could happen? Is there another source of electrons to stabilize that positive nearby? Well, we have the double bond. That means I have the potential for resonance. See how resonance comes back in. And I now have 2 possible positive carbons that could react with the chloride. Well, which one is the correct answer? Well, unfortunately, that depends on the circumstances that we run the reaction under. Okay? Okay, give me a second here. What we're looking at here is a thermodynamic versus kinetic issue. Okay, so what I want to do right now is kind of flag this as thermo versus kinetic. Okay, and I actually have a whole another video that last semester someone asked because we kept saying thermo versus kinetic. Okay, so I'm going to link out to that video so you guys can watch that. And it's got a little bit more information than you probably want to see, but it's all relevant for this first unit. Okay, so what do we mean when we're looking at thermo versus kinetic? Well, what we're looking at is an energy diagram, which you should have gotten out of 152, okay, second semester general chemistry, though they may not have actually shown you what's happening within it. What we have is our reactants and our products, and we look at the difference in energy between our reactants and our products. That is our thermodynamics. So the more exothermic, the lower in energy our products, okay, lower products, the more exo, okay, and the more likely that that is going to be a thermodynamic product. Okay? But what you should remember from second semester Gen Chem is it's not all about thermodynamics. We also get at how fast. Okay? And that speed is dependent on the activation energy, which is the height of that energy barrier to start your reaction, and that peak is our transition state. Okay, well, that speed depends a lot on structure when it gets into organic chemistry. How do the pieces interact? Do they interact in such a way that they lower the energy of the transition state? If the transition state becomes lower, that reaction becomes faster, even if it has a higher product energy. Okay, so what we're looking at when we talked about that previous situation is that we have one reaction that says we get a thermodynamic product. And then we have another reaction where the activation barrier is lower, but the product energy is higher. So we actually have competing products. We have a thermodynamic product that is very low in energy as the final product. And then we have a kinetic product, which is relatively higher in energy. So what we would have to go through and do is look at our reaction and say, okay, looking at our products, which of those is more stable? The more stable product is your thermodynamic product. If we're trying to find the kinetic without saying, well, it's the opposite of the thermodynamic, we'd have to look at the transition state for the reaction. Sometimes we can cheat and look at intermediates. Okay? And that's a lot of what the thermodynamic versus kinetic video is looking at, is several different reactions and saying how do they vary between kinetic and thermodynamic, and trying to get you to piece out and look at each of those mechanistic steps and saying how does that adjust your reactivities. Okay, so because I've got it here, I'll real quickly draw this out, and I'm going to draw it out invisibly, so it's all of a sudden going to pop. So what we've got now marked out here are the relative energies of each of our things. Because we're running two reactions that are both starting with the same starting material, we get one reactant well. This is then going to continue on to form our intermediates. Okay, well, when we look at those intermediates, we'd have to rank them according to their stabilities. The carbocation is the most reactive thing in each case, and sorry, I don't like that color choice, is the most reactive thing in each case. So what we would do is say, okay, which one is lower or higher in energy? Well, we have a secondary carbocation with resonance versus a primary carbocation with resonance. The secondary is lower in energy, hence I would draw its energy well a little bit lower. When we go to the product, we would then evaluate the most reactive thing present, and the most reactive thing present is actually going to be our alkene, our pi bond. Okay, so we'd have to say, okay, well, what makes those pi bonds different in energy? Well, the top one, we have a terminal pi bond, and the bottom one, we have an internal. The internal is more reactive, the internal is lower in energy because it's more stable than the terminal, and we end up seeing the energy wells as shown. If we then went through to try and draw out an energy diagram, we'd end up with something along these lines. And according to our Hammond postulate, our transition state is going to be closer in energy to the species that is closest to it. So if we look at the red one, start off, the transition state for the reactants are roughly the same, so there's no real big difference there. But when we look at our intermediates, the intermediate is actually closer to the transition state, which means the transition state is going to be closer in energy to the intermediate, okay, which seems kind of a silly statement, but it gets us some pretty powerful conclusions here. That powerful conclusion being the transition state for our thermodynamic product is higher in energy, which means it's a slower reaction. If we propagate this all the way out, we would then see our final products, and we'd have our kinetic product. It's going to form first or fastest because the activation barrier is smaller. We also have the thermodynamic product. Whoops, that was supposed to be a color change. A thermodynamic product because it is lower in energy than the other product. So how do we tell which reaction or which product is going to be formed? A lot of this is going to come down to the experimental conditions. If we run the reaction with a short amount of time, well, time being involved in it means we should expect the thing that involves time, we would expect more of a kinetic product. If we give it lots of time, now time isn't a variable, and we would expect the lowest energy product, or our thermodynamic product. Okay? Time is kind of a weird thing, particularly when we're running reactions, because our reactions happen in fractions of seconds, okay, or fractions of seconds. So time isn't a really good comparison. Typically, the extra comparison that we end up using is our energy, or the temperature at which we run the reaction. If we run at very high temperatures, what happens? Okay, well, every case, regardless of the condition, the kinetic forms first. So boom, I now have kinetic. But if I have a very high energy, what happens? The reverse reaction is also more likely. So what ends up happening, I reverse the reaction, I make it back to my starting material, and I now have the potential, although small potential, to go up the thermodynamic barrier. When I get product into the thermodynamic product well, that reaction is now so high in energy that I cannot reverse that reaction. It is irreversible. Okay? Because of that irreversibility, I end up with that product. So what we're looking at is how do the conditions force reversibility or irreversibility. Sometimes it can be the reagents, sometimes it can be temperature. The higher the temperature, the more reversible. That's because all reactions go faster at higher temperatures. If we drop the temperature, we now prevent or make it more difficult to climb that initial activation barrier. If we can't make it on that thermodynamic barrier, then I'm going to end up with the kinetic product primarily, and the thermodynamic product as a minimum. Okay? So it's looking at how can we change those conditions and manipulate them to get the product we want. Okay? And this is usually where this first kind of concept pops up, is with this type of alkene addition reaction. You will also see it in the Diels-Alder. I'm kind of hoping Brian will be able, Dr. Woodrum will be able to do a good job with this, so we shouldn't have to panic too much here. But in my kind of spin, what you want to do is, if we see a reaction works, we want to break that down into what happened. Okay? We know this reaction happened. How does this reaction happen? Okay? There's a video on this that kind of walks through and gets at those same general ideas. I'll also link out to that in this little white space before we kind of click through this. Okay, so as we click through, what we want to do is think about the bonds that are broken, the bonds that are formed, where are charges, are there partial charges, what happens if we draw resonance. All of these things need to be kind of constantly spinning through our brain. And yes, that's a challenge, and that takes time and practice, but that's the whole point of second semester. Okay, so before we look at the when question, let's look at what. Okay, notice that we had 3 pi bonds to begin with, and we end up with only 1. Okay, so our result is that we could say we broke 3 pi, and we formed 1 pi. Okay, but that's kind of knowing a little bit more about what's going on. So it's probably easier for you to go through and say that really what you probably see happening is that we broke 2 pi. Okay, hopefully you kind of get that idea. The next part is we made some new sigma bonds. Okay, where those sigma bonds are is going to be another question. Okay, but let's just go through and say it's these 2 sigma bonds. Okay, because ultimately it is. And that's 4 different things happening. If we think back to at least how I presented substitution reactions, we had a leaving group leave, and we had the nucleophile attack. 2 things happened, and we ended up with 3 possible results. If I have 4 things happening, the possible ways that those 4 things happen makes this a very challenging mechanism to interpret and discover. Okay? And this is where resonance really plays kind of a beast of a role here. Okay, what is that role? Well, if we go back to our structures and say, well, can I draw resonance? I can put all of the electrons on that carbon, which then means that carbon becomes positive. Well, if that carbon is positive, I'm going to want more electrons traveling towards it, so I can do that resonance and that. What happens to the other double bond? Well, if I have a negative down at the low end, I probably want to have a positive here, so I'm going to have those electrons travel up there. Oops, come on. What's the result? Have I made or broken any pi bonds? Okay, well, if I draw out just the official resonance structures, well, I'm going to have to redraw them all. What do I get? I get, come on, pen. I get a negative, positive, negative, positive, negative, positive. Are there any pi bonds present? Well, no. Okay. What does that mean? That means I don't really break pi bonds. If I use resonance, or my understanding of resonance, I could say there were no pi bond breakage. It was pi bonds just shifting around. That means no chemical reaction occurred. The sigma bond is where I want to keep my focus, which then means only 2 things happen. How and when those 2 things happen becomes the next question. I phrase this in a slightly different way than you'll see presented in your textbook, because I want you to think about how we figured out which of these 2 mechanisms occurred, and that's what the lab is all about. Do we make the first sigma bond and then the second, which I'm calling a DA1, matching kind of the conditions of our substitution type 1 mechanism, or our SN1, where it was stepwise? Or do we make the first sigma bond and the second sigma bond at the exact same instant, or simultaneously, like we did with the SN2 reaction? Okay, well, we don't really know. This is where we would need to go to experiment and see what our experiment told us. Okay? And that's where some of the design of the experiment comes into play. Okay? So, before I completely skip on, that's kind of where we're going to leave that and let lab kind of tease, or let those of you in lab tease out those kind of final answers. And then we'll finalize and wrap up the Diels-Alder reaction with the quote-unquote answers to how the reaction works and the potentially easiest ways to predict these products. It is not easy to predict these products because there's a lot of spatial awareness that has to go into these types of reactions. Okay, so if you have a hard time predicting your Diels-Alder reactions, build a freaking model. That's why I require them, though I never insist that you buy them, but you should be using them, and that's why. It's to allow you to see how these things can happen and what kind of directional changes happen with the model. Okay? After that, we kind of stumble into the review. Those of you that had me in first semester were probably like, oh God, stop talking, because there was way too much reactions that happened through here. And unfortunately, we're going to be running at kind of that same pace through here now. Okay, but I try to break it up a little bit differently and group things according to patterns that kind of come out of them. If we look at our addition reactions with electrophiles, almost all of these involve some kind of cyclic intermediate. Okay, because we're forming a ring, we have slightly different conditions. We no longer have the ability to do sigma bond rotation, which then means we get a much more selective product. Okay? The more selective the product is, the more likely you'll see these reagents, because it's going to make one thing or two things as opposed to 4 or 5. Okay? So, some of your cyclic intermediate reagents in chapter 12, if we're going to form a 3-membered ring, bromine, MCPBA, diazomethane, and your mercury compounds are all going to be forming a 3-membered ring. Okay? There is a review video posted on Canvas already that's breaking down how to identify the structures and how it's going to fit into these categories. Your tetra intermediates also happen in chapter 12, and that's your hydroboration followed by oxidation reactions. Okay? Again, we're still following the same pattern. We have an electrophile, we have a nucleophile being added to the double bond. It's just where those pieces are coming from. The last category, which in our textbook is kind of oddly placed in my opinion, moves into chapter 24, and that's looking at these 3 reagents: osmium tetroxide, potassium permanganate, and ozone. All 3 of those form 5-membered intermediates, or cyclic intermediates, before moving on to the final product. Okay? With all of these reagents, you are ultimately responsible for knowing what the product is, so what things are added to the double bond, and then their spatial arrangement relative to each other. The idea in the breakdown set up online, and that I'll kind of go through here, is getting you to look for those patterns and try and spend less time on the memorization of the reagent. Ultimately, you need to know the reagent, you need to know the result. What I'm trying to do is provide you the tools of predicting in a slightly different environment without having strictly memorized. If you strictly memorize, it will work for exam 1. It might work for exam 2. By the time you hit exam 3 in the final, you're going to start to be wishing you'd come up with some other context for how these reactions worked. Okay? So, in our cyclic tri-intermediates, the big thing that kind of stands out here is that your electrophile, whatever that species is, has a secondary ability to act as a nucleophile at the same instant, which is kind of weird, because those are counterintuitive or counter-objective things. The electrophile needs to be positively charged. the nucleophile needs to be negatively charged. Okay? So when we look at our reagent, one of the things that we're going to first need to see is that positive. The positive is our primary reactor when we look at our electrophilic additions, because we are reacting with a pi bond, and a pi bond supplies electrons, okay, first and foremost. So one of the very first things that needs to happen is those electrons need to come out and react with an electrophile. Okay? For the electrophile to be positive, something must be taking electrons away from it. That's the role of our leaving group. Okay? So that in and of itself is kind of our standard reaction. If we compare that back to the acid-base addition reactions, it's spot on. It's the exact same. The one thing that is now new and special about this cyclotri-intermediates is that that electrophilic atom also has a lone pair of electrons, okay, which is special because as the electrons from our alkene come out, we start to build a positive charge on the other carbon, okay, a large partial positive. Well, if I have electrons on my electrophile, I have a partial negative. Because the spatial approximation here is so close, those electrons can immediately share down, and we end up forming a three-membered ring. Okay? That's kind of the nuts and bolts of your cyclotri reactions. What happens after that stage then has a lot to do with the stability of that three-membered structure. If it is stable, okay, then we can potentially hold on to it and keep it around for a little bit. This is our epoxidation reactions. If it is unstable, then it will immediately get attacked by a nucleophile. Okay? Where does that nucleophile come from? That's typically found in the solvent somewhere. Sometimes it is the solvent. Sometimes it is the leaving group. Okay, so we have to be careful. We can't just assume, well, there's an extra species. It may be a natural product of the previous step. A leaving group took electrons. Well, what does a nucleophile have? Electrons. So a leaving group could very well be a nucleophile. It's a little bit of a challenge to kind of work through. This is why looking at the reagents and what results come out of those reagent reactions, that's important. Okay? Notice that I have two pathways, so I'm going to clear everything here. I have two pathways going on. I have one going to the left and one going to the right. What I'm trying to show here is that with the double bond, we are reacting pi electrons. Those pi electrons are located above and below the plane of the atom. That's because they're in p orbitals. Well, depending on where those electrons are spending arbitrarily their time and where the electrophilic atom seems to come close to the molecule, I'm going to see the electrophile form its bond on different sides of the pi bond. Depending on the structure, those sides may appear to be different, which then means I get the potential for two products because there were two possible attacks, okay, or two possible sides for the reaction to work. If I can't tell the difference, then the relationship between those two products is identical, as it is in this case. But if I go through and say change that to A and B, well, now what I'm going to end up with is not identical products, but enantiomers. Okay? So this is where your stereochemistry aspect comes into play. You need to be looking at these possible reactions and how the reaction works. Not just, oh, I form a trans product, but why and how did you form that trans product? The kind of memorization thing that you can tag onto this, you are reacting an alkene. An alkene has two reactive sides. Okay? Not sites, but sides. 2 reactive sides means 2 products. Okay, simple as that. Okay. So, some of the reagents that fall under this, bromine. Okay, why does this work? Bromine is electronegative, starts to pull those electrons away. That means one bromine becomes positive. There's my electrophile. But that bromine also has lone pair electrons. So I have an electrophile with electrons, matches my pattern. Okay. Diazomethane. Okay. I'll leave you to draw out the Lewis structure and prove this, that you're looking at something very similar. Notice that I did attempt to kind of hint that the carbon is the one that we need to keep our focus on. Okay, that's going to be the one that's going to act as our electrophile and our nucleophile. Other reagents. Okay, most people tend to freak out when they see this structure and they don't recognize it as the same thing as MCPBA. Okay, the PBA is the important part. That is peroxy. Or actually, we don't even need the B. Really, all we need are the P and the A. It's peroxy acid. Okay, peroxy is that bond. The acid is sort of that. So if I have a peroxy acid, it's going to be very likely that my electrophilic atom is that oxygen to form a 3-membered intermediate. Okay? And then the last one, the mercury oxides, or the mercury acetates, will end up going through and doing something very, very similar. Okay? We have a great leaving group in the acetyl groups. Okay? The OAC. This is O, and then this group is AC. Okay? Is a really good leaving group. Okay, why is it a good leaving group? Erase the bond. Erase the bond. The electrons. Oxygen being more electronegative than mercury should take the electrons with it. And we have, oh Lord have mercy, we have resonance again. Okay, that makes that a great leaving group. Well, if it leaves, the mercury carries a positive charge. Mercury as a metal, particularly a transition metal, messed up chemistry, also has lone pair electrons. Those lone pair electrons can be used to donate back into the structure to form our 3-membered ring. Okay, so we're again trying to find kind of patterns and work with those patterns to our structures. Tetra intermediates, the boron reagent is going to do something similar, except that when we look at the boron reagent, the big problem with it is that if we look at our leaving group, okay, or our electrophile, let's start with that. Our electrophile is the boron, okay, and that's because the boron is sp2 hybridized. It has an empty p orbital, and that's going to be our electrophile. Okay, so our electrons can come out and react. But just as we saw in the previous case, we then need to have a leaving group. Well, what do we have as a leaving group? Okay, we would have H minus. What can you tell me about H minus being a leaving group? The point of a leaving group is to stabilize the negative charge. Hydrogen being tiny cannot stabilize the charge. Hydrogen being not electronegative cannot stabilize the charge. Hydrogen not having any other atoms doesn't have resonance, doesn't have induction. There's no hybridization. That is a shitty, I need to work on that. That is an ARG leaving group. Feel free to call me out on that in class. Okay? That means that leaving group cannot exist on its own. So instead of it leaving out into the structure or out into solution, it immediately locks back down to our carbon structure. Okay? We have a large positive charge building, a large negative charge building. Okay? And what we end up doing is this kind of 4-membered transition. Okay? One of the things you'll notice is with some of these reagents, you need to do an extra step. The boration reaction is one of those. Okay? You are not required to know this mechanism. You are required to know the stereochemical results. Okay? Your second step of your hydroborations is an oxidation, and that oxidation is using peroxide. Peroxide will come in and it will do a direct substitution of an OH for the boron containing piece, not necessarily BH2, but the boron containing piece, maintaining stereochemistry. Now, that's what I'm trying to show with those wedges here. Okay, maintain stereochemistry. This is kind of a rare circumstance. Where is it coming from? It's coming from two pieces, peroxide and its reactivity, and the boron, okay, because of that empty p orbital. It's immediately allowing the peroxide to directly coordinate in, sort of, maintaining the stereochemistry. We don't see a backside attack. It just kind of locks in place, kicks one out, replaces it immediately. Okay? So you can think about that as a stability argument. I will be telling Brian about Dr. Woodrum about this, because there's some practice problems here. Hopefully he can work through some of those with you, maybe get you more familiar with that reagent. Okay. Your cyclopenta intermediates, this is where chapter 24 comes into play. You've got your Diels-Alder reactions, and then you also have this kind of odd, like, single section on osmium tetroxide, ozone, and permanganate. You will also see reference in the textbook to this, I think it's thiosulfate or sulfite compound, and a periodate compound. Technically, you're responsible for those. You won't see any direct questions from me about them. Typically, where those show up are in reference to OSO4. So if you just remember saying OSO4 gives you this product, you don't need to know what those secondary reagents are. You've got it nailed down. Okay? In all of these cases, what we're looking at is pretty much a 3-atom structure. And that 3-atom structure is the thing that's going to then coordinate to our double bond. Okay? That's going to end up giving us a 1, 2, 3, 4, 5-membered ring. What happens after that usually turns into a complete cluster arg, but you aren't super responsible for it. You're more responsible for what the end result is. And I know that's not satisfying, but your textbook does do a good job of looking at the mechanism for most of these. Take advantage of that and see what you can get out of it. Oh, and here's a nicer image with the pi bond showing that coordination with our alkene. Okay, so we can see kind of that mesh up with it. The Diels-Alder reaction, very, very similar. Whoops, sorry. Very, very similar. We've got our double bond now reacting with some other reactive atoms. The Diels-Alder, though, gets us a 6-membered ring. Okay? Whereas all of these other reagents that we're looking at within this section are generating 5-membered rings. But we're still focusing on that same kind of general idea. Okay. The syn dihydroxylation mechanism, this is looking in this case at the OSO4 reagent. Okay, remember as we form that ring structure, we would end up with this, whoops, I don't want to highlight that whole thing. We end up with our 5-membered ring. Okay. Everybody focuses there, and then they stop focusing on the next sequence of steps. And that next sequence of steps, this is where you can see a variety of reagents. Okay, whoops. First and foremost that I've seen is the reagent, nothing. Okay, will this reaction continue on its own with nothing? I don't think so, but for some reason it's listed. You can see peroxide show up in there. You can see, what's the other one? the HSO4 minus, okay? So bottom line, there's a bunch of extra reagents that can kind of carry this through. What you are responsible for remembering is that when you carry it through and you get rid of the metal, this is organic chemistry, we don't understand crap about metals, okay? When you get rid of that metal, you will replace it with alcohol groups, and those alcohol groups, you'll notice, are on the same side of the structure, okay? We have to be a little bit careful here because now I have a sigma bond and I can rotate about that sigma bond. So be aware of that kind of stereochemistry mess with your brain, because that is something the ACS exam will do, and that is something that I will do. Okay? You won't always necessarily see them drawn on the same side. You just have to realize the stereochemistry, when the double bond is reacted, is maintained. After the reaction is finished, we can do rotations. Those rotations are not going to change the relative position of those groups. What do I mean by that? If I did do a rotation, if I did this right, maybe you can ask Dr. Woodrum about this. You may look at this and then say, well, this can't possibly be the product because those are arranged in opposite directions of each other, okay, which couldn't possibly have happened. But if we look really carefully, all that's happened is I took that carbonyl group, or that carboxylic acid, and I rotated about the double bond to set up that structure. Okay? So they are one and the same, even though they appear, or one of them appears to be wrong. So be careful about sigma bond rotations after a reaction has occurred. Okay? I don't know why I have that predicted product at the bottom, because that is the reaction shown above. Okay? Next one is moving into permanganate. Permanganate, number one, does the exact same thing as osmium tetroxide, as long as it is cold and dilute. Okay? One of the kind of problems of potassium permanganate is that it will also do other chemistry if it is not cold and dilute, which can be considered an advantage. Okay? So permanganate is a very, very strong oxidizing agent, and it is very hard to stop at the dihydroxylation. So kind of our lead into that, if we can't stop, don't stop. Keep going. So if we go through and look at our possible reactions, we would end up with something along these lines. Okay? And we'd now say, okay, well, what can happen now? Oops. Okay, well, what ends up happening is we end up cleaving that all the way out. Okay, and we end up with a full-on double bond structure. Well, how and why does that happen? Okay, a lot of that has to do with the concentration of the reagents. We're now in a situation where I don't have enough to kind of just cleave off the permanganate, and so what happens instead is a cycloelimination reaction. We take the electrons out of the ring to form a double bond, which then shuffles electrons onto the permanganate. But now the permanganate has too many electrons, and it can shift the electrons outside. The result is we end up with the now alkene broken away from itself. Okay, and this is where we have to be careful. When we look at this structure, we might say, well, we only end up with one product. We only end up with one product because I started with a ring. What if it wasn't a ring? Those two carbons would not be connected in any way, shape, or form. Okay, so you have to be careful and watch out for how ring structures can mess with your perceptions. Okay, so if we look at this new functional group and try and come up with an approach to what's happening, we are in the presence of water or hydroxide, depending on our conditions. Well, that hydroxide is a strong negative. What would I look for to stabilize that negative? how about a positive? Okay, that hydroxide, through what's known as a nucleophilic addition reaction, which we haven't seen yet, okay, will attack that positive, forming what's known as an acid, as a hydrate. Okay, interesting feature of this is that our hydrate happens to be an alcohol with another alcohol, also known as a diol. Well, what can permanganate react with? It can react with the diol, particularly if it's present in high concentrations. We then form again our cyclointermediate. This time we're missing a carbon from it because our diol is I believe it's a gem diol because the alcohols are on the exact same carbon. And we would go through the same kind of elimination process. Keep doing that. We would take our electrons, take our electrons away from a hydrogen. Come on. And we end up, after the addition of H+, a carboxylic acid. So permanganate will oxidize like crazy. If there are any oxidizable hydrogens, we will remove those hydrogens and replace them with oxygens. You should be looking at this product and being like, okay, that looks reasonable, but what's this other carbonyl doing? What could it potentially do? Well, do we still have hydroxide and or water? Yup. Does the reaction stop here? Nope. Okay. The next one, ozone, and I promise I'll actually end with this one. Ozone does some kind of cool, crazy things here, and a lot of it is going to depend on this last step. Okay, so if we look at all of this mechanistic mumbo-jumbo that's happening through here, you're not responsible for any of that. What you're responsible for is that when we react ozone with an alkene, we end up with the alkene being cleaved or broken apart, okay, and replaced with oxygen bonds. The next question is, how many oxygen bonds? This reagent in red is the how many oxygen. Okay, so our purple, okay, ozone cleaves our pi bond, and then our red reagent tells us how many oxygens we need to be putting onto those carbons. Okay, so after our cleavage, we either go under reductive conditions, which is kind of an odd term. That reagent is TMS. That means we just replace the double bond with oxygens. Or we go under oxidative conditions, in which case, if there are oxidizable hydrogens attached to our alkene, or alkene former carbons, we will replace those hydrogens with oxygens. Okay, so in this case, under our peroxy method, okay, we will cleave the alkene and we'll replace any hydrogens on those carbons with oxygens. Quick-ish tip on how to do these reactions. If we redraw the structure, when we make that double bond really, really long, I think I lost a carbon. So let's just pretend I didn't lose a carbon. We can erase through the middle of that, draw on our oxygens. I'm just going to add another carbon down here. Okay. Highlight any hydrogens that would be connected to our carbon. Okay, the carbons of our double bonds. Okay, there's no other hydrogens. So that hydrogen, whether it's an hydrogen or an oxygen, is going to depend on that second step. Okay. Really, what I would say, is it DMS? Then leave it a hydrogen. If it's not DMS, make it an oxygen. So in this case, it is not DMS. So my product make sure I count my carbons appropriately this time. Ends up being this guy. Go through and count that out. 1, 2, 3, 4, 5, 6. I have my ring correct, and I end up with that product. And a short answer, this is where you leave it. Unfortunately, most of our exams are multiple choice, and they will not leave it as this result. What they will do is convert this into a prettier drawing. We can, look at the carbons of our rings or our chain. We've got a 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. At our second position, I've got an O. The 6th position, we got 1, 2, 3, 4, 5, 6. The 6th position, I have another carbonyl and an OH. Okay, and that would be my final product. So stretch the double bond, erase the middle, draw your oxygens. Best way to deal with your ozone reactions, and for that matter, your permanganate ones as well. After that, we'd be moving into the substitution elimination chapter of chapter 10, and hopefully I'll be able to get you a different video for that.